Hi, this is Alex from devstories.eu. GeoPandas, Episode 2 of 11. You are loading a 5 GB shapefile into memory, only to immediately drop 90% of the rows using standard pandas filters. Your RAM spikes, your script crawls, and you are wasting time. You can actually slice that spatial data before it ever leaves the hard drive. Today we are looking at reading and writing, fast I/O with Pyogrio. The primary functions you will use to get data in and out of GeoPandas are readFile and toFile. Historically, GeoPandas used a library called Fiona under the hood. It worked, but it was slow. Modern GeoPandas defaults to Pyogrio. Pyogrio is a direct, highly optimized interface to GDAL, which is the core C library that powers almost all open-source geospatial software. Pyogrio is fast by default, but you can force it to be much faster. When you call readFile or toFile, you can pass an argument called useArrow set to true. This tells Pyogrio to handle the data using Apache Arrow memory structures. Instead of reading the file and translating every single coordinate and attribute into a Python object one by one, the Arrow integration processes the data in large memory-efficient batches. This bypasses the usual Python overhead entirely. If you are dealing with millions of records, turning on the arrow flag turns a read or write operation that takes several minutes into one that takes a few seconds. But the most effective optimization is simply reading less data. A very common mistake is reading the entire massive dataset into a geodata frame and then using standard pandas indexing to filter it down afterward. This causes massive, completely unnecessary memory spikes. GeoPandas allows you to filter the data during the read file operation itself, which keeps your memory footprint flat. Let us say you have a file containing every building footprint in New York State, but you only care about the buildings around Coney Island. If you pass a bounding box tuple to the bbox argument in read file, the underlying C engine checks the spatial index of the file on the disk. It completely ignores any building outside that defined box. You get a tiny data frame containing only what you need, and your RAM barely registers the operation. If a simple rectangular bounding box is not precise enough for your needs, you can use the mask argument. You pass a specific geometry, like a complex polygon representing exact neighborhood boundaries, directly into read file. The engine evaluates this shape and will only load rows that intersect your polygon. It's slightly more computationally expensive than a basic bounding box, but it's highly accurate. Spatial filtering covers the geography, but you can also filter the standard attributes. The readFile function accepts a where parameter. This takes a standard SQL clause as a string. If you only want buildings tagged as residential, you pass a string stating the type column equals residential. GDAL parses the SQL statement and filters the rows at the C level before passing anything to Python. You can even combine a bounding box and a where clause in the exact same read call to slice both geography and attributes simultaneously. Here is the key insight. Pushing your filters down to the read operation means the heavy lifting happens in highly optimized C code, not in Python memory. The absolute fastest way to process spatial data is to never load the parts you do not need. Thanks for spending a few minutes with me. Until next time, take it easy.